So an important part of SHM oscillators when they are damped is the exponential relationship of their amplitude. This may be something you've done in maths. If you haven't yet already, you will do before your end of your A-level. But this does come up in SHM now, so I'm just going to go through the basics of exponential decays. It comes up lots and lots in physics. It comes up in radioactivity, it comes up in capacitors, it comes up in sort of attenuation of radiation as well. So we're going to look at the basics today. It's a phrase that often is used. People go, oh, it's increasing exponentially. It's often misused. We normally look at exponential decays in physics rather than exponential increases, which I'm going to look at the context today. So when two things are related in an exponential way, the rate of change is directly proportional to the magnitude. The magnitude, how big it is. And the magnitude, the rate of change is obviously how quickly it changes. So an example of this would be populations. If we look at bacteria, if we have double the bacteria, we expect double the number of new bacteria in an hour. Because there's twice of them, they're all going to reproduce at the same rate, and therefore if we have more of them, we're going to expect more new ones in an hour. Human populations as well are also roughly exponential, and you might have read about in the news about the coronavirus is exponential as well. If double the amount of people have it, you expect double the rate of infections as well. But with SHM oscillators, that's what we're going to look at today. So I'm going to draw a quick graph here. We have time on this axis here, and we have displacement x on this axis. So this is a lightly damped situation where it completes many oscillations before coming to rest. So this is our initial amplitude here, A, and you can see it slowly decreases over time. Now, as the other video I put a link to indicated, that the time period stays the same, approximately the same, for a lightly damped oscillator. So what we want to do is we want to show, is this an exponential decay or not? So there's two different ways of doing this, and I'll show you the first way. So the first way is that it loses an equal proportion of its magnitude in equal periods of time. So an equal proportion of magnitude actually I might just change that, it's probably a bit easier to understand if I go fraction of magnitude in equal periods of time. So what I need to do is I need to look at equal time periods. So let's say that this has got a time period oscillating backwards. We'll do this in seconds, and we'll have this of 2 seconds, 4 seconds, 6 seconds, 8 seconds. So we can see the time period, the time for one complete oscillation there is 2 seconds. Now I'm going to make up some numbers for this so that the maths works out nicely. And I'm going to say that the displacement here at this point, x, is equal to 16 centimetres. X here is equal to 12 centimetres, so I would just be reading this off this x-axis. That would be 16, that there would be 12, that there would be 9 centimetres, that there 6.75 centimetres, and this one here 506. Now you might think, why have I chosen those weird numbers, but hopefully that comes up in a sec. Okay, so we want to show that an equal fraction of the magnitude is lost. Magnitude is lost in equal periods of time. So I'm just going to do a table here. I'm going to go time here, 0, 2, 4, 6, 8, and then I go my magnitude, which is x, how big it is at that particular period of time. So what I'm going to do here is I'm going to put these numbers in here. So when it is 0 seconds, the amplitude is 16 centimetres. Put some units here. Be careful, you've got to make sure it's the amplitude as well. It's the amplitude which is exponential, not just the displacement. You can't take any points other than the peaks or the troughs of the graph. And then 12, and then 9, and then 6.75, and then 5.06. So that's our decay. You can see it's decreasing, but we want to see that the decrease is proportional to the magnitude. So what I'm going to go in this column here is I'm going to calculate what xn divided by xn minus 1 is. Okay, so if xn here is 12, so I'm going to go 12 divided by xn minus 1. The previous one is 16. So 12 over 16, 0.75. I'm going to do the same in this one. I'm going to go 9 over 12 equals 0.75. 6.75 divided by 9. I'm not doing this in my head. I worked this out beforehand. 0.75, 9, and then I'm going to go 5.06 divided by 6.75. So we can see that in equal periods of time, in every 2 seconds, it loses the same fraction of its magnitude. So it's losing a quarter, or we have 0.75 remaining after each 2 seconds. There is a little trick to this, because what we could do, we don't have to actually read the numbers off the x-axis. Because we know the time period is the same, we can just write the number of oscillations. So we can just go 0, 1, 2, 3, 4. As long as these are equal periods of time, it doesn't matter there. Okay. Now, the other way of doing this is sort of do the reverse. So what you do is you look at equal periods of time, or so you work out how long it takes to go down to a certain fraction. So you might remember this from radioactivity, but I could do an example here where I go, how long does it take to half? Or 16 to half is 8. And then we could go, so that is x equals, that's 8, and then we've got to look how long it takes to go to 4, and that is going to be about 9 there. So if we say that's that there is 4.5, we'd expect that to be 9. So rather than looking at the amount, the fraction it goes down in equal periods of time, what we're looking at here is what are the periods of time it takes to decrease by the same fraction. So this is how you would show that something like radioactivity decay is exponential, because you can see, well, you can use either method, but you can see that it takes equal periods of time to decrease by the same fraction. Here I'm doing a half. The reason I've shown you this way, AQA in their exam love a nice table like this saying what's the relation, show that the relationship is such and such a relationship here. But also the problem you've got with a lot of SHM oscillators is that the decrease is quite small. So you're looking at very, very small changes. So the fraction is not a half, it's not a half, it's not a quarter, so it's a lot harder to see. So I recommend you use this method here, and this is a way of showing that something is an exponential relationship.